Okay, well, let's take a look at this last example from our lecture on implicit functions and implicit differentiation. Here we're asked to use implicit differentiation to find the equation of the tangent line of ln of xy equals 2x at the point 1 comma e squared. Let's go ahead and start by taking a look at this particular function in the equation explorer. So ln xy equals 2x is what we're after. Ln xy equals 2x. Okay, so this is the graph of that implicit function. Of course, it's not an explicit function. And we can see that it indeed does have a value at x equals 1 that looks to be e squared. E is about 2.718-ish. So when you square that, you get something in the neighborhood of 7. And 1 comma 7 appears to be really somewhere in this neighborhood. Probably be nice if I adjusted my window settings to -2 to 2 in the x direction. And now we can definitely see that 1 comma 1, 2, 3, 4, 5, 6, 7-ish is on the curve. So 1 comma e squared seems to be an acceptable value. We'll check that in a minute. But if we were looking for the equation of the tangent line to the curve at that point, we would expect something to have a positive slope and have a y-intercept that's somewhere near 0. So let's go ahead and take a look at this now on pen and paper. We'll go ahead and maximize this out and take a look at what we have. So let's first take a look at this function ln xy equals 2x, and just check to make sure that 1 comma e squared is really a point on that graph. Well, if I plug in 1 and e squared in for x and y, then the argument inside the natural log would be e squared. And we'd be checking to see if that was equal to 2. Well, by laws of logarithms, we can take the 2 out in front, and natural log of e is of course 1, so 2 is equal to 2. So indeed, since I get a true equation, excuse me, a true equal sign, that means that this point is indeed a solution to that equation. So let's go ahead and see if we can find the derivative at a point now. So the first thing we'll do is implicitly differentiate the function by applying the differential operator to both sides of the function. Okay, so when I apply the differential operator to the left-hand side, I can see it's definitely a chain rule, where inside of the chain rule I have a product rule. So the first thing I'll do is derive the outside function, take the derivative of the outside function, so that would be 1 over xy, and then I would take the derivative of the inside function, so I'll just leave that as d by dx of xy for this step. Here I have the derivative of just a function of x with respect to x, so we can call that derivative 2 because, of course, that's a linear function with slope 2, so its slope is everywhere 2. Okay, let's talk about the the product rule here now. We have 1 over xy. If we apply the product rule to this setting, what we would have is the first times the derivative of the second, so first times d by dx of y. Well, that's just dy dx, right? And then the second, adding that to that, the second times the derivative of the first, d by dx of x, well, that's just a 1, right? So it looks like we've got something we can simplify now and solve for dy dx. So when I distribute the 1 over xy to the first term, the x's cancel, and I get 1 over y dy dx, plus when I distribute the second term, the y's cancel, I get 1 over x, and that's all equal to 2. Well, that implies then that 1 over y dy dx is equal to 2 minus 1 over x. And then multiplying everything by y on the right-hand side, we'll end up with dy dx equal to 2y minus y over x as my derivative of this implicit function. Okay, so we've got a derivative expression now. Let's see if we can find the slope at this particular point. So what is dy dx in this case? Oh, my pencil is running out of lead, sorry. What is dy dx evaluated at the point in question? X equals 1, y equals e squared. Okay, well, let's go ahead and use our equation. It's going to be equal to 2 times e squared minus e squared over 1. Well, that's just 2e squared minus e squared. So that's just e squared. And turns out then the derivative at the point 1 comma e squared is actually equal to e squared. So similar to the exponential function, the derivative at this point is equal to the value of the function at this point, or the value of y at this point at least. Okay, let's go ahead and use that information now to build the tangent line. If we want a tangent line, we know that it's of form y equals mx plus b, but of course the slope of the function at that point is e squared, so y equals e squared x plus b right now would be what we know about the equation of the tangent line. We'd like to solve for b now. We need a y-intercept, but we have a point on that line, right? It's got to pass through 1 comma e squared, so that's the way I'll solve for it. I'll put y in for y and e squared, in for x a 1, and therefore we can see that b has to be equal to 0 because if I subtract e squared from both sides I get 0. So the equation of the tangent line must be e squared x. Let's go back to Desmos and see if that's really the case. Sorry, not Desmos, but the Equation Explorer. So let's go ahead and put in the function y equals e squared x. And that looks really nice. It does seem like it does pass through the function or have the same point as the function, and it appears tangent to the function at that particular point 1 comma e squared. Might be even more fun to take a look at a window that goes from, I don't know, say 0 to 2, and oh, I don't know, from a y sense, let's just go from negative 1 to 10. And we get a good, nice, close picture there that seems to confirm that we have indeed found the right equation for the slope of the tangent line. Okay, well that's about all I wanted to do in this video, finish off this example problem. Good luck with your homework on implicit differentiation.